6.2, significance testing for proportions. Now, what is a significance test? A significance test is a procedure in which you compare a claim or hypothesis to observed data. The claim is going to be a statement about a parameter, like what the population proportion or what a population mean is going to be. We express the results of a significance test in terms of probability, measures how well the data and the claim agree with each other. So, for example, suppose a basketball player claims that he makes 80% of all of his free throws. He's probably exaggerating, but if we wanted to test this claim, we could easily have him shoot a bunch of free throws and keep track of the percentage. Now, what would that look like? Well, so here, let's assume that this is the proportion of free throws that he makes versus proportion of free throws that he doesn't make, right? Now, we could have him shoot a bunch of free throws. And we see after a long enough time, he's shot a whole bunch of free throws. He's made 87 and he's missed 26. So maybe there's something to his claim. Right now, we're not really sure. It seems that he makes more than 3/4, but is it close enough to 80% to where we can, say, okay, yeah, fine, you're right. Now, what we've just done is we have stated both a null hypothesis and an alternative hypothesis. When we're testing claims, we have to take a very pessimistic approach to things when stating our hypothesis. We state what is called the null hypothesis and the alternative hypothesis. The null hypothesis is what we assume is true. It's what we weigh our evidence against. So we're assuming that the guy's claim is true. We assume that he makes 80% of his free throws. The alternative hypothesis is what we are trying to find evidence for, right? So the alternative hypothesis is what we think might be true. So if we thought he was exaggerating, then our alternative hypothesis was that he's lying. Now, the alternative hypothesis can take 3 different forms. You can have the alternative hypothesis in which you think the parameter is less than whatever value you're getting. So if we think that he is shooting less free throws than he says he does, you could assume that it is more. So maybe we're not giving him the benefit of the doubt. Maybe he's actually a better free throw shooter than he says he is. Or we're not sure either way, so we just assume he's wrong. Now, in this example, we believe that the null hypothesis is that the proportion equals 0.08. The null hypothesis is always going to be P equals some value. The alternative hypothesis, what we're trying to test, is always going to be P is either less than, greater than, or just simply not equal to that very same value. In this instance, the alternative hypothesis is that the true proportion of free throws that he shoots is less than 80%. Now, when we state this hypothesis, when we state the hypotheses should express our hopes and suspicions before we actually look at the data. So we are already kind of cheating, but not a big deal right now. Hypotheses always refer to the population, not a sample. So we don't make predictions about a sample. That's just boring. That's not interesting. Nobody cares. Instead, it's much more interesting to make a prediction about the overall population. And we use the sample to either disprove or fail to disprove that statement. So the idea for these tests is to compare the evidence against our hypotheses, right? So an outcome that would rarely happen if the null hypothesis is true, well, that means that there's good evidence that the null hypothesis isn't true. For example, if we assume that he, makes 80% of his free throws, and out of 100 free throws, he only makes 20, well, if he's telling the truth, then that's a really unlikely outcome. Therefore, he's probably not telling the truth. The probability computed by assuming the null hypothesis is true, that a statistic would take a value as extreme or more extreme than the one that we actually observe, is called the p-value of the test, the probabilistic value of the test. So in general, small p-values are evidence against the null hypothesis. Basically says the probability that this would happen if the null hypothesis is true is very, very small. It's incredibly unlikely. Large p-values fail to give evidence against the null hypothesis. Basically, the probability that this would happen is, if the null hypothesis is true is reasonable. Now, there's no rule for how small the p-value should be, so we can usually set our threshold as low as we want. That threshold that we decide as our line, if it's less than this, then we're going to say he's lying. If it's bigger than this, then he's telling the truth. Whatever that threshold is, we call our significance level, and we use the symbol alpha, the Greek letter alpha, for that symbol. In general, if the p-value is smaller than alpha, then we say the data is statistically significant at that level. If that's the case, then we can reject the null hypothesis and conclude that there is convincing evidence for the alternative. Otherwise, if we get a value that is not statistically significant, then we fail to reject the null hypothesis, and we conclude there is not enough evidence to show the alternative hypothesis is true. So in general, if the p-value is less than alpha, then you reject the null hypothesis. If the p-value is greater than or equal to alpha, then you fail to reject the null hypothesis. Notice you never confirm the alternative hypothesis. That's not what we do. We do not confirm that our suspicions are true. We just reject the hypothesis that they're not, or we fail to reject the hypothesis that they're not. I know it's kind of weird. So is everything about this class. Now, when we draw conclusions from significance tests, we always hope that we're correct, but since everything we're doing is based in probabilities, then of course there's a chance that we're wrong, just like everything else. So there's two types of errors we can make. The first one, type 1 error, is when we reject the null hypothesis when we weren't supposed to. Basically, if we say, nah, you're lying, but he was actually telling the truth, then that's called type 1 error. If we fail to reject the null hypothesis when it wasn't true, when the alternative was in fact true, then we commit type 2 error. Basically, if he is lying and he doesn't make 80% of his free throws, if in fact he makes less than 80%, but we don't have enough evidence to call him out on that, that is called type 2 error. Now, the significance level, alpha, for any fixed level test is the probability of making that type 1 error, right? If we say the probability, or if we say that if the probability of getting our results is less than 5%, then we're going to reject them, then of course that suggests there's a 5% chance that he could be telling the truth anyway, and we chalk it off as him lying. Now, it's always important to consider the consequences of committing this type of error when you're choosing your significance level. For example, in this example, if we commit type 1 error, if we say he's lying when he's not, then the stakes are very low. It wouldn't be too hard to imagine a type of scenario in which the stakes are very high. So, for example, if you were making an algorithm that was going to determine if a student was cheating on a test, the stakes for calling out a student cheating on a test, especially in college, are very high. So you would want the probability that you make type 1 error to be very small. You don't want to accidentally kick a student out of school when they're telling the truth. Now, how do we actually do one of these tests? So, just like with confidence intervals, we have to check the same conditions as we did before, right? So we have to check to make sure everything's random. It comes from a random sample or well-designed experiment. Of course, we have to, the data's got to be independent as well. We have to check the 10% rule that I just told you about last section, that we got to have less than or equal to 10% of the population as our sample. And there's the large counts. That's to make sure the central limit theorem is true, right? We have to have at least 10 successes and 10 failures in our sample. Now, once we confirm that, we can get what's called a test statistic. And a test statistic measures how far a sample statistic diverges from what we would expect if the null hypothesis was true. It's calculated by whatever our statistic is minus that parameter divided by the standard deviation of that statistic. Yes, it's a z-score. Then, using the table, we find the p-value for that z-score, and boom, done. So in our example, he made 87 out of 113 attempts. So 87 out of 113. So he made 76.9%, or we'll give him the benefit of the doubt, 77% of his free throws. out of 113 attempts. So if we're using this formula, we have 0.77 as our statistic, 0.8 as our parameter, and then divided by the standard deviation of the statistic, which, again, is the formula that we had way back, p times 1 minus p over n, all underneath the square root. So if we're doing this by hand, I say by hand, but I'm still using a calculator, 0.77 minus 0.8 divided by square root of p, the statistic, p hat, 77.313. And we get a z-score of negative 0.7577. Now, again, it says go to the table to see what that would be. So, sorry, I lied to you. It's actually square root of p times 1 minus p, not p hat times 1 minus p hat. So it's 0.8 times 0.2, not 0.77 times 0.23. So you use the population, right? You use the stuff from the null hypothesis. So with that, you should get a test statistic of 0.79 or negative 0.797, and then you go to your normal table and you find 0.797 or negative 0.797, which I guess you just do negative 0.8. So negative 0.8, 0.21186 would be our value. So the probability of him only shooting 87 out of 113, if he's telling the truth about scoring 80% of his free throws, the probability of him getting this result is actually relatively high. It's just over 20%, right? It's just over 21%. So there's a 21% chance that this would happen, given that he's telling the truth. So for this, we would probably fail to reject the null hypothesis. We would probably just be like, okay, fine, you're telling the truth. Now, that seemed like a lot, right? Finding all that seems kind of tedious. There was an easy way to do confidence intervals. Isn't there a way to do significance tests in the calculator? Of course there is. So, just like before, you got to remember a few key important things, right? First, you got to remember what class you're in. You're in statistics. Then you got to remember what it is you're doing. You're doing a significance test, a stat test. Then you got to remember what you have. I have one proportion. Here you go. So it'll ask you a couple questions. Okay, what does the null hypothesis say is true? He says he makes 80% of his free throws. How many did he actually make? Well, he made 87 out of 113. Okay. Do you think he makes more than that? Less than that? Or are you just not sure? Oh, well, I think he makes less, right? I think he makes less than 80%. Okay. Well, the probability of him making less than 80%, or making the amount of free throws he made, given that he actually is telling the truth, is 0.211968. Basically, exactly what we got before. The p-value is 0.211968. Probability that he makes 87 out of 113 free throws, given that he is making 80% of his free throws, is about 21. So, very reasonable. Now, p-value of a one-sided test is the area in one of the tails of a standard normal distribution, right? That part hopefully was made obvious by the way we looked at the table, and we're only looking at the area that was on the left. So typically the alternative hypothesis is greater than or less than a specified proportion. A two-sided test, though, has an alternative hypothesis which says the proportion is just not equal to whatever he says it is. Now, the p-value in this test is the probability of getting a sample proportion that is as far or farther away from p, or p naught rather, in either direction, right? You're not sure if he makes more or if he makes less. You just think he's lying, right? So as a result, you'll have to find the area in both tails to get the p-value. Now, I just showed you that usually we'll be using the TI, or we'll use the calculator to do all that for us, but it's important that you understand that the p-value that you're given there is split up in the two tails, so you might want to take that into consideration. If you are trying to affirm strongly one way or the other, it might be a good idea to use a one-sided test rather than a two-sided test. One-sided tests are stronger, right? They are more definitive. So maybe doing a two-sided test will tell you which direction to make your one-sided test, and then you can do a one-sided test on top of that to be sure. But in general, one-sided tests are stronger than two-sided tests. Now, part of the reason for that is because a two-sided test basically gives you no more or less information than a confidence interval would give you, right? Confidence interval tells you that it's probably between these two values. A significance test tells you whether or not it's likely that it's outside of a given range. So it wouldn't necessarily be a good idea to do a two-sided significance test unless you just really don't know what you're going for. In general, try to go for a one-sided test. You'll accomplish more. Now, we talked about type 1 error earlier. We never talked about type 2 error, and it's important as well. So the power of a test is what is the probability that it rejects the null hypothesis when the null hypothesis is supposed to be rejected, right? High power is good. It is inversely related to the probability of making type 2 error. Of course, type 2 error is when you fail to reject the null hypothesis when the null hypothesis wasn't true. Makes sense. So basically, if someone tells you beta, which is the probability of making type 2 error, then the power is just of the test is just 1 minus that number. You will not be tested on trying to find out what beta is. So it's not something that we'll spend a whole lot of time on, but as long as you know that the power of a test is the probability that you correctly reject the null hypothesis, and the way to find that is 1 minus the probability that you incorrectly reject the null hypothesis, then you'll be good to go. Calculating beta itself is not something that we're ever asked to do on the AP test, or within the scope of this class at all. Maybe in college. If you take statistics in college, you'll have to do it, but no. Now, there's the last bit here called the 4-step process. I'm actually going to make a separate video on this altogether. I actually had a different playlist about this specifically. I'm probably going to delete that playlist and refine it, so it'll be a little bit more updated. But the 4-step process is basically the way that you will be expected to answer confidence interval questions and significance testing questions on the AP test in a free response format, right? And I'll go into much greater detail on this aspect specifically in a separate video. So anyway, in the meantime, I hope this was helpful.